Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the correlation coefficient, rho, in the context of simple linear regression. Okay. So, first, consider the following model. Let's talk about the model we are going to be dealing with. So we have y, random variable, we have beta 0, we have beta 1, we have x, and epsilon. Okay, where, and here go the assumptions, where epsilon we assume is a random variable with a normal distribution, mean 0, variance sigma square. And this assumption that we're going to make here is slightly different from the one we have made for the classic simple linear regression model, right? In this case, we're going to assume that x itself, the predictor variable, is a random variable, also with a normal distribution, a particular mean mu sub x, and with its own variance sigma of x, or sigma sub x square. Okay, so that's an important difference between what we had before. Before we thought, okay, these values are given, right, and they are constants. Now we're thinking about them as numbers coming from a random variable, right? Okay. Another important assumption here will be that these two random variables, epsilon and x, are independent. Okay? Okay. So, from our assumptions, right, we can easily find the expected value of y and the variance of y. And since what we want to do is finding the correlation coefficient, we will need those quantities at some point. So we might as well find them. Okay? So let's find the expected value, the mean of y. So expected value of y, and let me introduce a notation here, just similar to the notation we're using for x. Let me use mu sub y to refer to the expected value of the random variable y. So it would be the expected value of beta 0 plus beta 1 times x plus epsilon, right? Okay. So we have the expected value of a sum, that's a sum of expected values, right? No problem. Let me copy paste this. So expected value of beta 0 expected value of beta 1 times x, expected value of epsilon, right? And the expected value of a constant will be the constant itself. So we have beta 0 here. The expected value of a constant times a random variable will be that constant, beta 1. We get to factor it out, and then it would be the expected value of x. So let me use mu sub x to refer to that expected value. And we know that the expected value of epsilon is 0 by assumption, so that would be mu sub y. Okay? Okay. Now let's find the variance. Let me borrow this. And instead of expected value, we have variance, and just like in the case of x, let me use this notation, the sigma notation for the variance of y. So it would be sigma sub y square. Okay? Okay. So it would be the variance of that model that we assumed, right? So now we have the variance of a sum. Are these guys independent? Oh yeah, they are. By assumption, epsilon and x are independent, and this is just a constant, and the variance of a constant is 0. So we are going to only have the variance of beta 1x plus variance of variance of epsilon, right? Okay, and let me mention that we get to do this by independence, right? Okay. Now we know that since we want the variance of a constant times a random variable, we have to square that constant here, and we have the variance of x, which is sigma square sub x, right? Plus variance of epsilon, which happens to be sigma square. Okay. Okay. Nice. So, as we said at the beginning, our goal would be finding the correlation coefficient between x and y. Okay? So let me remind you, and you know this from statistics 256, right? That the correlation between two random variables x and y is the covariance divided by the product of its standard deviations, right? So rho is the same as, oops, not what I wanted. Covariance between x and y divided by sigma sub x times sigma sub y. Okay, so let's find the covariance. Once we have the covariance, we will have the expression of the correlation coefficient. Let's find the covariance between x and y. Okay, so again, from statistics 256, you must remember that the covariance is by definition just a particular expected value, right? It's the expected value of a cross product, if you will, a very special cross product. It would be the random variable x minus its mean, mu sub x, times y minus mu sub y. So that is by definition the correlation, the covariance. The expected value of that cross product is by definition the covariance between these two random variables x and y. Okay. Okay. So let's do a little bit of algebra here. So what we're going to be doing is we're going to be plugging in the expression of y here, okay, and we also have the expected value of y. Remember, we obtained that, okay? So let me copy paste that line, and then we're going to substitute for y. Remember that y is just beta 0, right, plus beta 1 times x plus epsilon, right? Remember, let's copy paste that. Instead of y, we have that, and for the mean of y, we have this, beta 0 plus beta 1 times mu sub x. Okay. There we are. No problem, right? Easy. So now note that when we multiply by this negative 1 here, we're going to have beta 0 minus beta 0. So these guys will cancel out. Okay? So let me copy paste here and simplify that a little bit. So we said that we are not going to have those beta zeros. Now note something else. We could factor out that beta 1, right? Beta 1x minus beta 1 mu sub x would be the same as this, beta 1 times x minus mu sub x, right? Same thing, right? So all we did was beta 0 minus beta 0, they cancel out. Then we have beta 1x minus beta 1 mu sub x, and that epsilon also survives, right? We just factored out that beta 1, and that's it. So no mistakes so far, right? We're good. Okay. What else? Okay, so that expression there, we could rewrite as beta 1 times x minus mu sub x square plus x minus mu sub x times epsilon, right? So let's do that. So this would be just beta 1 times x minus mu sub x square plus x minus mu sub x times epsilon, right? You guys agree? Okay. So, what else? Now, note that what we want here is the expected value of a sum. So, that's the same as the sum of expected values. Let's just say that. Okay, no problem. Now, let's try and simplify these expressions. That beta 1 we get to factor out, and that's exactly what we're going to be doing next. Let me factor out that beta 1. Okay. Now, we have the expected value of a product, but since x and epsilon are independent by assumption, the expected value of a product of independent random variables is the same as the product of expected values. So let me just point that out. By independence, we get to do the following. The expected value of that product is the product of expected values. Right? Okay. Now, by definition of variance, right? The expected value of x minus mu sub x square, that's the variance of x by definition. So that guy is sigma square sub x. Now, the expected value of epsilon is 0. So that product is just 0. So we have nothing. Make sense? So finally, what we have shown is that the covariance between x and y, this particular case, given our assumptions in our model, is beta 1 times sigma sub x square. Therefore, rho, which happens to be the covariance divided by the product of the standard deviations, happens to be just beta 1 sigma sub x square divided by sigma sub x times sigma sub y that is just, you know, this is the same as sigma sub x times sigma sub x. So what we're going to end up with is just beta 1 sigma sub x, no square, right? Cancel that one out, and that's what we end up with, right? So what we have shown is, again, in this case, for this modified version of the simple linear regression model, where now we consider the predictor variable x a random variable, well, if x and y are random variables, we get to compute the covariance between them and the correlation coefficient, rho, right? And in this case, the correlation coefficient is beta 1 times sigma sub x divided by sigma sub y. Okay, so that's the summary of what we have done here together in this video. This expression will be useful in the near future in another video when we talk about a quantity that will help us measure the strength of linear associations. That quantity is called the coefficient of determination, and it is related to rho. Okay, but we will talk about that later. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.